So let's talk about permutations when I cannot have repeating elements. As we said, I'm going to use a permutation to count the number of discrete units that I can have when the order in which they are selected makes a difference. We found out that when the elements can repeat, when selecting an element out of the population does not remove it from the population, that I use the formula n raised to the power of r. But what happens if selecting an element out of the population does remove it from the population? We have to revise our formula just a little bit. So what happens if the house numbers cannot have repeating elements? I can say that this first position that I would actually have 10 different options that were available to me. The second position, because I removed one out of the population, would only have 9 options available to me. The third one would only have 8 options available to me, and the fourth one would only have 7. And this equals 5,040. So if I cannot have repeating elements, I've reduced my number from 10,000 down to 5,040. Let's see if we can find a formula that we can use to calculate permutations when no repeats are allowed. So just looking at my house numbers, it seems pretty obvious that the first value is the number in the population. It seems like the second value is the number in the population minus 1, and the next value is that minus 2. And so if I were to take n as the number in the population, and I multiplied it by n minus 1, and then I multiplied it by n minus 2, the question is, how far do I have to go? Well, we stopped at 7. And 7 is actually the population minus the number of elements that I was choosing. For this example, it would be 4. Well, 10 minus 4 actually gives me 6, and so I need to add 1 back in. And so if I were to create a generic formula, I would say n times n minus 1 times n minus 2 all the way down to n minus r plus 1. And this is when I would end my formula. If I wanted to simplify this formula, this is actually going to become n factorial divided by n minus r factorial. Maybe I should write the r, represent the r with the lowercase r that I have. So this is a formula that we can use if I want to count permutations when repeating elements are not allowed. So let's see if this formula will work on my house numbers. I can represent this as n permutations of r with the same value of n and r. So this is going to be n factorial divided by n minus r factorial. And if I wanted to do 10 in my population, and I am going to be choosing 4 out of this, this is going to be 10 factorial divided by 10 minus 4 factorial. This gives me 10 factorial over 6 factorial. If I were to plug these values into my calculator, I would come up with some amazingly large numbers. So I'm going to try to simplify this a little bit more. I know that 10 factorial is actually equal to 10 times 9 times 8 times 7 times, well, 6 factorial. And then if I have a 6 factorial underneath it, those two would cancel out, and I end up with 10 times 9 times 8 times 7, which gives me the 5040. I know that because that was my original equation right there. So it would appear that this formula is actually working. So let's try it with something else. Let's say, for instance, that you wanted to buy the homeowners of your new development. You wanted to buy them puppies from the pound. And so you go to the pound and you find out that there are 15 puppies in the pound. This would give us a population value of 15. And let's say, for instance, that you have 6 new homeowners that are moving in. And so I'm going to choose 6 of those 15 puppies out of the pound in order to give to my brand new homeowners who have bought in my development. So I ask the question, does the order in which they are selected matter? Yes, because the first person, the first homeowner, is going to get to pick their puppy, and then I'll have the second homeowner pick their puppy, and the order in which they are selected does matter. The second question that I ask myself is, can there be repeats? And if the first owner picks the only Chihuahua, then that Chihuahua is removed from the population, and the second homeowner can't choose it, which means that we cannot have repeating elements. So I'm going to have 15 permutations of 6. So this is going to give me 15 factorial divided by 15 minus 6 factorial. This is going to give me 15 factorial divided by 9 factorial. I'm pretty sure that if I were to mark it down, times 9 factorial divided by 9 factorial, I can reduce those out, and this is going to give me 3,603,600. So this is the total number of ways that my 6 brand new homeowners can choose one of the puppies in the pound. And if I don't believe that this works, let's just work it out manually. I have 6 homeowners and 15 puppies, which means the first homeowner would be able to choose from 15 puppies. The next homeowner would only be able to choose from 14, and then 13, and then that is 3 homeowners. That would be 4 homeowners. That would be 5. My 6th and final homeowner would only have 10 puppies to choose from. And this actually looks remarkably similar to what I ended up with after I worked out or simplified my permutation formula. So just to sum up, I deal with permutations when the order in which the items selected matters. License plate numbers, house addresses, passwords, the order in which the items are selected or matters. But we find out that there are 2 separate categories: when I can have repeating values and when I can have no repeating values. With repeating values, we're just going to do the population raised to the number of items that I am selecting out of the population. When I have no repeating values, I'm going to take the factorial of the population and divide it by n minus r factorial. These are the 2 formulas that we can use with permutation.